Here's my solution to the Lunar Rover problem. As I talked about in my other video, the scenario here is that you're on the moon and you've got a lunar rover. You've got to go from your base camp at point A into this crater, somewhere between point P and point Q, to pick up some lunar rocks. After you pick up your lunar rocks, you're going to head to point B to fix a beacon that's malfunctioning. The challenge for the kids, and for the teacher, to be honest, is to find the location of point C that minimizes your total distance for your trip. First step is for the kids to make a scale drawing of the situation on graph paper. A over here is where you're starting, and you're going to somewhere over on this vertical line within the crater to pick up your moon rocks. I decided to start at 10. Thought in the middle would be a good place to start. Once you pick up your moon rocks, you're headed over to point B to fix that malfunctioning beacon. In order to find those two diagonal distances that I have in blue pen, I had to use the highlighted blue legs, make a right triangle, and use the Pythagorean theorem. And then the same thing on the segment on top. I had to use the highlighted pink or purple highlighted segments as the legs, and then Pythagorean theorem to find the diagonal segment. For my first attempt, using the coordinate 0, 10, you can see my results down here. The first segment was 30.2, second segment 19.2, and then the total number of kilometers that the trip would take. I tried a few other points, trying to figure out that minimum distance. I stuck with integer values, and I think that initially with the kids would be a good idea as well. I then did a whole bunch of other calculations with a little technology help that I'll show you later in the video, and I filled in my table for all of the possible integer values for the location of point C. It goes from 0 to 19. So there you can see all the total distances for the lunar rover. If you make a graph, you can see where you should look, somewhere around 12. So using integer values, I would pick 12 as my minimum distance, right above 49 kilometers round trip. Next part of the activity, trying to minimize the time it takes for the trip. Now you might initially think, well, wait a second, if you minimize the distance, you're also going to minimize the time. But that's not the case, and that's one of the things I really love about this problem. Once you pick up your rocks in the crater, your rover will go slower. So you can't go as quickly. Before you get your rocks, you can go 8.9 kilometers per hour. But after you get your rocks, you're slowed down to 5.5 kilometers per hour. And that to me is just adds a great twist to this problem. So I did the same thing I did before. I started with 10, and I figured out the distance of, figured out the time for each part of those trips, and then the grand total, 6.798 hours. And then I did a few more, again, step by step. Coordinates of point C, this time at 11, and then at 12. Made and filled in another table with all of the possible integer locations for point C, with a little help from technology. And there's my graph. So it looks like it's going to be somewhere around 14, the minimum time. Here's where I changed the activity a little bit. I wanted to get the kids to write and solve general formulas. In the previous examples I just showed, they had to do it for specific locations of point C. Well, here we've changed them to variable locations for all your different points. And then what that allows you to do is to write and solve formulas. That's one of my big complaints about our textbook. A lot of times we just solve these equations for x that don't have any real meaning or context. Here's a great opportunity for kids to solve a formula that has a meaning and a context. And same thing for time, using general generic points, writing and solving formulas to find the total time. Those come in handy when you use some of the other technology resources that I'll show you in just a minute. I said I had some help filling in those tables, and what I eventually did was I eventually wrote a spreadsheet that would do all of the calculations for me. So here you can see the results of the spreadsheet. You've got your distances for each part of the trip, the total distance. You've got the time for each part of the trip and the total time. In order to do that, I had to write and solve formulas to get the spreadsheet to actually do the calculations for me, and I rounded them to 3 decimal places. That was a lot of fun to me. Writing and solving those formulas, not something I get to do all that often. It was a bit of a challenge, but it was fun. Well worth it. Hopefully this will really convince kids, the power of the spreadsheet. Once you write that formula, you can do many, many, many calculations very, very quickly. And you can see how much time it saves you. The other thing I did was down at the bottom, I told the spreadsheet to look for the minimum value within the column. So you can see here that 49.308 is the minimum, and that's 12 seconds. No, that's not. That's the location of point C at a y value of 12. It's 49.308 kilometers. As far as the minimum time, 6.79 hours. And it looks like that is at a vertical location of 14 for point C. Within the spreadsheet, kids can also, and teachers I guess, make graphs. And they can also make graphs for the total time. Now as you see here, the answers might not be integer solutions because it looks like maybe it dips down a little further. So that could cause for further investigation on the part of the students. What happens if you're allowed to use numbers other than integers? I did another technology piece. I wrote some graphing calculator programs. The first one allows the user to input any y value for point C, and the calculator will do the calculations for them. I've had a little bit of trouble getting it work. There we go. So here's the program Lunar. It's asking for the y value of point C. So I started with 13. There's the distance for the first part of the trip. There's the distance for the second part of the trip. And there's total distance for both parts of the trip. There's the time for the first part of the trip, time for the second part of the trip, and total time for the entire trip for that distance. If you want to try a different point C, run the program again and enter some new coordinates. When writing this program, I had to use those same formulas that I did for the spreadsheet. And that's the part that I added to this activity to bring a little technology into it and to get the kids to write and solve formulas in a real-world context rather than just solving for X. And I wrote another program. I might just show it like this because I've had a little bit of trouble with it, with the video playing in PowerPoint. But this one's called Lunar Min. This is a great chance to use a loop to run through the program. What I did, I programmed the loop to run for all the possible values of C from 0 to 19. Initially, I did it using whole numbers. I played around with it a little bit since, and it can be edited to look to the nearest half, 0.5. You could even change that, and you can go as specific as you want with your decimal places. But when you run this program, there's not much to see, but it's running a loop in the background, and it's looking for the minimum distance and it'll give you the location of point C, 12, and then the total distance, a little bit over 49 kilometers.